-7. So that's the final.
That's the total final.
Oh.
We just won for the 2 kilogram mass.
Well, we said -1.4 was the final velocity?
Yep,
And that's the final velocity for which one?
for both of them,
For power.
because they stuck together. So for the 2 kilogram mass, what is its momentum?
Wait, they stuck together, so it'd just be the same, right?
Same velocity.
Same velocity. So then it'd just be 8 times 1.
8 times.
8 times 1.4.
What's the formula for momentum?
MV?
Yeah. And what's the mass of the 2 kilogram mass?
Oh, 2. Whoops. 2 times 0.
And the velocity?
1.4.
Negative.
Negative 1.4. So negative 2.8.
Negative 2.8. And so the impulse exerted on the 2 kilogram mass is negative 10.8 Descartes. Newton seconds, kilogram meters per second, depending upon your mood. The impulse on the 3 kilogram mass is going to be something minus, is it negative 15? Well, the mass is 3, the velocity is negative 1.4.
Negative 3.3, or no, would be positive. You said, what did you say? The 15?
This is P initial,
Mm-hmm.
and this is I went for the 3 kilogram piece of it. The final, so it's the mass, 3 kilograms, times negative 1.4, the velocity.
Negative 4.2.
So what's negative 4.2 minus negative 15?
Negative 19.2.
No. What? That would be plus negative 15.
Oh, never mind. It's 11.
What'd you say?
10.8.
10.8. What? Wait a second, that's negative 10.8, that's positive 10.8. What are the chances? I know that the total momentum doesn't change, so they better be opposites of each other. They better add up to 0. Questions to hear before we extend this?
Is it always going to be opposite? Like one's going to be negative, one's going to be positive?
Yeah. They're transferring. What one loses, the other one gains. It's like they collide. One of them's a pickpocket. When one loses, the other one gains. All right, let's extend it. What I want to know is, what is the change in the kinetic energy of the system? Well, I can treat it as one object afterward. I can treat it as 2 objects if I want to, but one object just makes a little bit more sense. So I got 1/2 times 5 times 1.4 squared minus, they are definitely 2 objects before the collision, 1/2 times 2 times 4 squared plus 1/2 times 3 times 5 squared. This is my final momentum minus my initial momentum. Total. We'll get totals here.
Wait, why is the 1.4 positive?
What's the formula for kinetic energy?
1/2 mv squared.
Yes. That's not a vector, it's speed. But if you tuck the negative in there, when you square it, it goes away anyway. Other questions about how we got what we have written on the board at this point?
Is there a reason we use brackets, or? I know it's not any difference, I'm just asking.
It was my mood. I because I had enough other parentheses in there, I wanted a little flair. I got style, that's why. All right. Does everybody work this out yet? This is. Supposed to make a getting you an easy comment, but it seems inappropriate, even if it is just a lot.
$22.
I'm not buying that.
So 5.4, 5.14 times, so 5 times 1.4 is 7. 7 squared is 14.
There's a problem there.
Oh,
Only the 1.4 is squared. If you multiply by 5 first and then square it, you've now squared the 5.
I've screwed up my house.
Is it 32.6?
I'm not buying that one either. Unless there's a Karos error on the board. Alright, this is 16. This is
I missed that.
Oh, my.
37.5.
Whoops.
That's more difficult to do in my head.
That's not quite it. I thought that was that. Never mind.
Okay. I know the answer's gotta be negative. That's why I dismissed this so quickly.
Negative 48.6.
Negative 48.6 units?
Wait, how are you getting 9.8?
Yeah, it's a,
That's not 9.8.
it's a 4.9.
Oh, whoops, I didn't do that. Whoopsie.
Is it still negative 48.6?
Oh, I just.
Or did you did the whole thing, okay. Units? What is it what we were finding?
The Newton, the kinetic energy. Well, that's what we're saying.
So,
Joules.
change in kinetic energy, so the units are
Joules.
joules. All right. And lost kinetic energy. Where did it go?
It's a closed system, so it had to do something.
Yes, it did.
Did it transfer to another machine?
Can
There's only those two objects.
is there a ground? Like, are they on the ground or are they just in space?
Space. The universe is just these two objects.
Does it, like when they hit, is the, well, I guess if they stick together, there's no friction or anything.
Right.
Does it create heat?
They'll both heat up some. The energy gets lost into the internal kinetic energy. There is a relationship between kinetic energy and temperature. So this is sort of macroscopic kinetic energy, and when they collide, they'll warm up some. Just like if you clap your hands will warm up just a little bit. Or a lot, depending on how hard you slap. All right, so in a perfectly inelastic collision, I'm gonna lose kinetic energy. Matter of fact, in a closed system collision, perfectly inelastic collision is the maximum amount of kinetic energy lost. Any questions before we extend this just a little bit more?
So negative 48.6 joules is the maximum amount of kinetic energy lost.
Yes, in this particular two-body collision.
Now, I don't know how big an energy unit of a joule is. Is that a lot or a very tiny amount? I know it's negative. Like, would that add up to like 1 degree or?
Boltzmann constant is. What is exactly look up? Let's do it this way. I'm supposed to there's a textbook floating around here.
What is a blowtorch?
I'm gonna go grab a textbook and we'll put it in terms of food calories.
This place is going crazy. Yes, that's- There we go.
All right, so negative 48.6 joules times 4.186. Just add it. There we go, 4.184. So what's that? It's gonna be a little bit more than 10. Well, we're doing a rough estimate here. More like 12-ish. So we'll just go with 12 calories. But these are physics heat calories, these are not food calories.
Is that a different amount than a food calorie?
Yeah, food calories off by a factor of 1,000, so this is 0.012 food calories. So, give you some sense of how much energy that is.
Pretty small.
Yeah. In terms of temperature, what are the chances he has a Boltzmann's constant? No, zero chance.
Is that a cooking book?
Yes.
What do you think, Mark?
It is temperature kinetic energy relationship. The kinetic energy is equal to, it's either 1/2 or 3/2, like at the moment. Boltzmann's constant.
This, that's right. 3/2 R/NA T, no, never mind.
No, 3/2.
That's what, yeah. Yeah, KB, or R over, yeah, so.
Yeah, there are
KB
variations, there's several variations on it.
Yeah, so 3/2 KBT, yeah, that's it.
Okay, and what's KB?
KB equals 1.38 times 10 to the negative 23 JK negative 1.
Joules per Kelvin. Those two capital Ks are different. So that would be, something's off there. 10 to the negative 23rd?
Yeah, that's what this is.
All right, I'll have to get back to you on how much temperature that would raise it. Wait a second. It depends on the substance itself. We have the mass. So the energy, oh, yeah.
Obviously.
Quick thermodynamics here. This is the heat. This would be the amount of energy you're either putting in or taking out. Mass, this is known as the specific heat, and that would be the change in temperature. So if we stuck in the 48.6 joules is equal to 2 times, and then it comes down to what is the material times delta T. So divide by 2 and divide by whatever the specific heat is here, which will be some single digit number, I believe. So potentially it's going to raise the temperature 4 degrees. Or raise lower, somehow there's an exchange there. I wish I'd thought of that one before that one, but oh well. All right, questions? Because I know what you're thinking. You're going, do we have enough time to bring in more math? Yes, we do. So we're gonna take that collision there, except this time we're not gonna lose any kinetic energy.
So it's gonna be a perfectly elastic collision.
Yes.
Yes. Okay.
Now, I guess there's a video where I talk about the naming conventions. It's, please watch that. Because what the language I'm using is different from other textbooks, which is different from, there's not a set language. So please be aware of that. As you read the textbook, what they call an elastic collision or an inelastic collision, frankly, I've dealt with too many textbooks, I can't keep which ones do which naming convention. So I came up with my own. The perfectly inelastic, perfectly elastic, I think are pretty clear. They're at the extremes. The ones in the middle, I just refer to as imperfect. So we're gonna do a perfectly elastic collision, which I will often abbreviate as PEC. Matter of fact, it's a one-dimensional perfectly elastic collision. I know my total kinetic energy, or sorry, my total momentum is -7. And that's gonna be equal to my final,
It's -7.
which is -7, which is 2, go ahead, stick the numbers in now, 2V2 final plus 3V3 final. I got 2 unknowns there. Now, it's a lot of writing, I don't feel like writing that much. So what I'm gonna do is I'm just gonna let, C equal V2 final. And, nope, I'm using D for something else. H is V3 final.
Now, you have -7, which is the total momentum,
Yes,
and you have 2 times
that's velocities.
so 2 times velocity final plus 3 times velocity. What is the right side of the equation?
This is the final momentum. It's, remember, momentum is mass times velocity, so this is M2 V2 final plus M3 V3 final. Where M2 and M3 refer to the 2 kilogram mass and the 3 kilogram mass respectively.
And that equals -7.
Yes,
Okay,
just like we got the -7 from just doing the initial.
right. Okay, got it.
Other questions right now? Conservation of momentum. But since perfectly elastic collision, kinetic energy is conserved, I know we have K initial equals K final. So my total initial kinetic energy, we just figured it out, it was 16 plus 37.5.
Yeah. 4.9 minus 16 plus 37.
Just want the initial.
Oh,
Is that 43.5?
Well, it'd be 53.5.
53.
Because it was 16 plus 37.
53.5, that's my initial kinetic energy. My final kinetic energy is gonna be 1/2 times 2 times C squared plus 1/2 times 3 times H squared. Writing the first one in the same notation, you got -7 is equal to 2C plus 3H. The more subscripts I write, the more apt I'm to make a mistake. That's why I do the substitution. 2 equations, 2 unknowns. This is definitely within the realm of this course. How do you solve it?
You have to make something equal to something, so you can substitute something.
All right. What do you want, what do you want to solve for?
Let's solve for C first.
C, all right. My recommendation, solve for one of the letters in the momentum equation. We're not dealing with squares to start with. So C is equal to -7 minus 3h divided by 2. I guess to put it in the intermediate step, -7 minus 3h is equal to 2c, and then divide both sides by 2. You now have this. It depends on if you like fractions or decimals, so I guess it's -3.5 minus 1.5h. I'm now going to take that and plug it into my energy equation there. So I had 53.5 equals 1/2 times 2, got that one in my head. Minus 3.5 minus 1.5 h squared plus 1.5 h squared. And now, we got a binomial we're squaring. So, quick refresher, if I have a binomial that I am squaring, what is it equal to?
A squared plus 2A
So this becomes 53.5 is equal to 3.5 squared plus 2 times 3.5 times 1.5 plus 1.5h, 1.5h squared plus 1.5h squared. That is the binomial squared. Now, if you're wondering what happened to the negative signs, stick them in if you want. That negative there will get squared and go away. I'll have a negative